August 7th, 2025, 0830 hours. Universal Time Coordinated. NASA Jet Propulsion Laboratory Internal Planning Document, JPL MM 2025-0341. Subject line, 3I/Atlas Perihelion Survivability Assessment. Quote, based on thermal stress modeling for nucleus approaching 0.25 astronomical units solar distance, fragmentation event probability estimated 92%. Expected breakup window, October 25th through October 31st. Recommend prioritizing observation resources for fragmentation documentation. Document classification, internal use only. Distribution, restricted to mission planning team. August 8th, 2025. Public NASA press briefing. Quote from briefing transcript. Interstellar comet 3I Atlas will reach closest approach to the Sun in late October. Like previous interstellar visitor 2I Borisov, we anticipate the object may fragment due to thermal stress during perihelion passage. This presents unique scientific opportunity to study internal composition of object formed in another star system. Public expectation established. Comet will break apart. Comparison case. Comet 2I/Borisov. December 8th, 2019. Distance from Sun, 2.006 astronomical units. Hubble Space Telescope observation. Documented nucleus separation into two distinct fragments. Fragment size ratio, approximately 3:1. Event confirmed by multiple independent facilities. Standard outcome for interstellar comets experiencing solar heating stress. 3I Atlas parameters. Perihelion distance, 0.255 astronomical units. Solar flux at this distance, approximately 15,000 watts per square meter. Comparison, 2I Borisov, fragmented at distance where solar flux was only 2,200 watts per square meter. 3I Atlas, experiencing 7 times higher thermal stress. Fragmentation prediction, logical extrapolation from established precedent. August 15th, 2025. European Space Agency issues Independent Fragmentation Forecast, ESA, Technical Memorandum, SCI OPS 2025-114. Modeling assumptions. Nucleus composition similar to solar system comets. Density 800 kilograms per cubic meter. Tensile strength 10,000 pascals. Conclusion. Nucleus structural failure expected at heliocentric distance 0.4 to 0.3 astronomical units due to thermal expansion, stresses exceeding material strength. Fragmentation likely during final approach phase before perihelion. 2 independent space agencies, 2 consistent predictions. Object will fragment. September 1st, 2025. Observation campaign planning initiated. Hubble Space Telescope allocated observation time, October 20th through November 10th. Primary objective per scheduling document. Document fragmentation sequence of 3I Atlas with high temporal cadence imaging. James Webb Space Telescope allocated near infrared camera time, October 27th through October 29th. Objective: capture thermal signature and composition variations associated with nucleus breakup event. Ground-based facilities coordinated. Very Large Telescope, Chile, Gemini North Hawaii, Keck Observatory. Combined observing time, 147 hours, scheduled specifically for fragmentation documentation. Resource allocation indicates institutional commitment to fragmentation hypothesis. Standard procedure: allocate premium telescope time to anticipated high-value events. 3I Atlas fragmentation classified as such event. Opportunity cost: other scientific programs delayed or cancelled to accommodate fragmentation observation campaign. Decision requires high confidence in predicted outcome. September 12th, 2025. Object distance from Sun, 2.7 astronomical units. Brightness, magnitude, 13.2. Photometric monitoring by amateur Temperature Astronomy Network detects no brightness variations beyond expected rotational modulation. Rotation period confirmed, 8.3 hours. Amplitude of brightness variation, 0.18 magnitudes. This variation consistent with elongated nucleus shape, not indicative of structural instability. Baseline structural integrity established. September 25th, 2025. Distance, 1.8 astronomical units. Increased solar heating begins. Surface temperature modeling predicts approximately 210 Kelvin. At this temperature, water ice remains solid, but carbon dioxide begins sublimation. Expected observable, increased carbon dioxide outgassing, creating visible coma. Actual observation, carbon dioxide production rate 28 kilograms per second. Coma detected but faint. Nucleus appearance, still point source, no resolved structure, no signs of cracking or surface failure. October 1st, 2025. Distance, 1.3 astronomical units. Hubble Space Telescope, pre-perihelion observation. Integration time, 600 seconds. Spatial resolution, 0.03 arcseconds per pixel. Nucleus diameter estimated 4.2 kilometers. Object appearance, single coherent body. No evidence of satellite fragments. No dust jets from discrete vents. No brightness asymmetries suggesting structural weakness. Image archived. Baseline condition documented 1 month before. Predicted fragmentation window, October 7th, 2025. Updated fragmentation forecast issued by NASA Ames Research Center. Revised model incorporates actual thermal response data from September observations. Conclusion unchanged. While nucleus has remained intact through initial heating phase, thermal stress increases exponentially during final approach. Fragmentation remains highly probable within predicted window. Most likely fragmentation date, October 27th, plus or minus 2 days. Confidence level stated 85%. October 15th, 2025. Distance, 0.7 astronomical units. Surface temperature, now approximately 260 Kelvin. Water ice sublimation threshold approached. Expected transition, carbon dioxide dominated activity to mixed volatile release including water. Ground-based spectroscopy confirms water vapor detection at 3.1 micrometers wavelength. Production rate 12 kilograms per second. Carbon dioxide continues at 35 kilograms per second. Combined outgassing produces visible coma approximately 50,000 kilometers diameter. Nucleus itself, still unresolved point source showing no morphological changes. October 20th, 2025. Fragmentation window opens. Hubble begins intensive monitoring. Observation cadence every 6 hours. Each observation 300-second exposure. Purpose: detect fragmentation event within hours of occurrence. Protocol requires immediate notification to community if multiple nuclei detected. Rapid follow-up by other facilities to characterize fragment trajectories and sizes. Alert system activated. Global telescope network standing by. October 22nd, 2025. Distance, 0.47 astronomical units. 9 days before perihelion. 2I Borisov fragmented at 2.0 astronomical units. 3I Atlas now 4 times closer to Sun, experiencing 16 times higher thermal stress. Hubble observation, 0700 hours. UTC, single nucleus, no fragmentation detected. Observation, 1300 hours. UTC, single nucleus, no fragmentation detected. Observation, 1900 hours. UTC, single nucleus, no fragmentation detected. Pattern continues. Fragmentation window open. Conditions met. Outcome, negative. October 25th, 2025. Distance, 0.32 astronomical units. Peak fragmentation probability date per original forecast. Surface temperature estimated 320 Kelvin. Thermal stress exceeds model tensile strength by factor of 2. Material failure prediction imminent. Hubble observation sequence. Images captured 0400, 0800, 1200, 1600, 2000 hours, UTC. 5 observations spanning 16 hours. Result all images intact, single nucleus. No fragments. No dust clouds indicating sudden structural failure. No brightness surge indicating large-scale volatile release from exposed interior. Internal NASA email circulation detected via Freedom of Information Act request filed November 8th. Email dated October 25th, 1800 hours, UTC, Goddard Space Flight Center to JPL Mission Planning. Quote, 5 consecutive Hubble observations show no fragmentation. Object now inside predicted breakup zone with no structural changes detected. Models may require revision. Recommend continuing observation campaign through perihelion plus 10 days, regardless of fragmentation non-occurrence. Email acknowledges discrepancy between prediction and observation. Email remains internal. No public statement issued. October 27th, 2025. Distance 0.26 astronomical units, 48 hours before perihelion. James Webb Space Telescope near-infrared observation. Integration time 4 hours. Data shows carbon dioxide sublimation rate 90 kilograms per second, water vapor 42 kilograms per second, nucleus temperature 350 Kelvin. High outgassing rates indicate intense thermal processing. Material strength under extreme stress. Fragmentation conditions optimal. Actual fragmentation absent. Webb images resolve nucleus as single elongated object approximately 4 kilometers long axis. No secondary components detected down to sensitivity limit of 500 meters diameter. Structural integrity maintained. October 29th, 2025, 07 hours, 47 minutes. Universal time coordinated perihelion. Closest approach to Sun, 0.255 astronomical units, 38 million kilometers. Orbital velocity at perihelion, 97 kilometers per second. Surface temperature peak, estimated 370 to 390 Kelvin, depending on albedo assumptions. Thermal flux, 15,300 watts per square meter. Comparison, Earth surface receives 1,360 watts per square meter at equator noon. 3i Atlas experiencing 11 times Earth's maximum solar heating. Material strength requirements extreme. Object response intact. Ground-based observatories worldwide targeted perihelion moment. Observations from 6 facilities across 4 continents. Mauna Kea, Hawaii. Cerro Paranal, Chile. La Palma, Canary Islands. Mount Stromlo, Australia. Sutherland, South Africa. Mount Graham, Arizona. Combined observation window. Perihelion plus or minus 6 hours. Objective. Capture fragmentation event in real time if occurs during observable period. Result from all facilities. Single nucleus detected throughout observation window. No fragmentation event documented. October 30th, 2025. 24 hours. Post-perihelion. Object now receding from Sun. Distance 0.27 astronomical units. If fragmentation occurred at perihelion, but during solar conjunction when object positioned behind Sun from Earth perspective, fragments would now be separating with measurable angular distance. Hubble observation. High-resolution imaging specifically designed to detect fragments. Sensitivity. Capable of detecting components separated by as little as 200 kilometers projected distance at target range. Result. Single compact nucleus. No separated fragments. No debris cloud. No evidence fragmentation occurred during unobservable perihelion passage. November 1st, 2025. Distance 0.41 astronomical units. 3 days post perihelion. Thermal stress declining, but still exceeds 2I Borisov fragmentation conditions. Very large telescope. Adaptive optics observation. Spatial resolution 0.05 arcseconds. Best ground-based resolution achieved for target. Image quality sufficient to resolve nucleus structure if multiple components present. Analysis of image data. Single coherent body. Elongated morphology consistent with pre-perihelion observations. No subcomponents. No evidence of structural damage. Comet survived perihelion intact. November 3rd, 2025. NASA public update. Press release. JPL 2025-321. Quote, Interstellar comet 3I Atlas successfully observed during perihelion passage. Object continues outbound trajectory. Data analysis ongoing. Release makes no mention of fragmentation predictions, makes no comment on structural integrity, makes no acknowledgement that predicted event did not occur. Information content minimal. Discrepancy between prediction and outcome unaddressed. November 5th, 2025. Scientific community response begins. Planetary Science Institute, Arizona issues research note. Title: Structural Integrity of 3I Atlas through Extreme Perihelion. Implications for Interstellar Object Composition. Paper documents. Fragmentation predictions from NASA and ASA. Actual observations showing no fragmentation. Calculated thermal stress exceeding modeled material strength by factor of 2 to 3. Conclusion section, quote, Either compositional models for interstellar objects require fundamental revision, or material strength properties significantly exceed current estimates. Observed survival of perihelion passage at 0.255 astronomical units suggests nucleus possesses structural characteristics unlike typical solar system comets. Mechanism providing enhanced structural integrity undetermined. November 7th, 2025. University of Hawaii Institute for Astronomy publishes comparison analysis. Data compiled. 2I Borisov fragmentation parameters versus 3I Atlas survival parameters. Borisov nucleus mass, approximately 200 million kilograms. Fragmentation distance, 2.0 astronomical units. Solar flux at fragmentation, 2,200 watts per square meter. Atlas nucleus mass, estimated 27 billion kilograms, 135 times more massive than Borisov. Perihelion distance, 0.255 astronomical units. Solar flux, 15,300 watts per square meter, 7 times higher than Borisov fragmentation flux. Summary: vastly larger object survives vastly higher stress, while smaller object fragmented under lower stress. Implication: fundamental difference in structural properties between two interstellar visitors. Material strength calculation performed. Tensile strength required to prevent fragmentation under observed conditions. Minimum 70,000 pascals. Comparison: typical cometary nucleus. Tensile strength from solar system comet studies, 5,000 to 15,000 pascals. Required strength, 5 to 14 times higher than standard comet material. Question posed in analysis: what compositional or structural characteristics produce this strength enhancement? Conventional explanation: higher rock-to-ice ratio producing stronger matrix. Calculation: rock fraction required to achieve 70,000 pascal strength, approximately 80% by mass. Observation data: spectroscopy shows ice-dominated composition with rock fraction approximately 20 to 30%. Contradiction identified between required composition for strength and observed composition from spectroscopy. November 10th, 2025. European Southern Observatory releases spectroscopic analysis from Very Large Telescope. October observations. Spectrum covers 300 nanometers to 2.5 micrometers wavelength range. Molecular detections: carbon dioxide, water, Carbon monoxide. Trace amounts. Dust continuum analysis indicates silicate dust grains present in typical cometary proportions. No exotic refractory materials detected. No metal-rich composition signatures. Composition assessment. Consistent with volatile-dominated icy body. Similar to solar system long-period comets. Material strength prediction based on this composition. 10,000 pascals maximum. Observed material strength requirement. 70,000 pascals minimum. Factor of 7 discrepancy. Unexplained. November 14th, 2025. Freedom of Information Act request filed by Independent Research Consortium. Target documents. Internal NASA analyses of fragmentation prediction failure. Structural models explaining perihelion survival. Correspondence between modeling teams regarding prediction accuracy. Meeting minutes discussing observational outcome. Justification for request. Scientific community requires access to institutional analysis of major predictive failure to improve future models. Request submitted to NASA Office of Inspector General. November 21st, 2025. FOA preliminary response received. Release timeline. Estimated 45 to 60 days for document review and declassification assessment. Responsive documents estimated approximately 240 pages, including technical memoranda, email correspondence, meeting summaries. Withheld documents estimated undisclosed number under exemption categories, including pre-decisional deliberative materials and proprietary mission planning information. Full release not expected until January 2026. November 25th, 2025. Distance from Sun 1.2 astronomical units. Object now beyond Earth orbital distance, continuing outbound. Hubble conducts follow-up structural assessment observation. Objective: determine if delayed fragmentation occurred. Some comets fragment hours or days after perihelion due to thermal stress propagation through nucleus interior. Image analysis. Nucleus remains single coherent body. Photometric brightness declining according to inverse square law of distance as expected for intact object. Rotational light curve. Amplitude unchanged from pre-perihelion baseline. Assessment. No fragmentation occurred during perihelion passage or in subsequent 27 days. Structural integrity confirmed throughout thermal stress episode. November 29th, 2025. Published predictions versus observations summary compiled by Max Planck Institute for Solar System Research, Germany. Document catalogs. 2 published peer-reviewed papers predicting fragmentation. 4 institutional technical memoranda forecasting breakup. 6 public statements from NASA and ESA indicating expected fragmentation. Total predictive statements. 12 from 8 different institutions and research groups. Observational outcome. 0 fragmentation events detected across 147 hours of dedicated observation by 9 independent facilities. Predictive accuracy, 0%. Discrepancy scale, categorical prediction failure. Institutional response analysis. Number of public statements acknowledging prediction failure, 0. Number of revised models published explaining survival mechanisms, 0. Number of technical papers addressing structural strength discrepancy, 0 from institutional sources. 3 from independent university groups. Pattern identified. Prediction failure generates no institutional follow-up. Independent researchers investigate. Institutional researchers remain silent. Information asymmetry noted. December 1st, 2025. Internal NASA memorandum obtained through confidential source, authenticated via metadata analysis. Document dated November 18th, 2025. Subject: 3i Atlas structural analysis implications. Content excerpt: survival of perihelion passage at 0.255 astronomical units requires material properties inconsistent with spectroscopic composition data. Three scenarios warrant consideration. 1. Spectroscopy misinterpreted. Actual composition differs significantly from analysis. 2. Material strength mechanisms not captured in current models. Unknown structural reinforcement present. 3. Thermal stress calculations incorrect. Actual stress experienced by nucleus significantly lower than modeled. All three scenarios present theoretical difficulties. Recommend formation of working group to address discrepancy before publication of post-perihelion analysis. Document classification for official use only. Public release not authorized. Working group formation mentioned in memo. Follow-up investigation. No public announcement of working group creation found. No meeting minutes released. No participant list published. No interim findings disseminated. Working group either not formed despite recommendation or operating without transparency. Either outcome represents deviation from standard scientific process where major anomalies trigger coordinated open investigation. December 5th, 2025, 3 months after fragmentation predictions issued. 0 public institutional statements addressing why predictions failed. 0 published revisions to structural models. 0 acknowledgement of 70,000 Pascal strength requirement versus 10,000 Pascal compositional prediction. Silence pattern established. Predictive failure documented. Institutional response absent. Question: when major scientific prediction fails completely, standard procedure requires analysis of failure mechanism, model revision, public discussion of discrepancy. Observed procedure: silence. Why does categorical prediction failure generate no institutional response? December 10th, 2025. Alternative analysis approach, published by independent research group at Leiden Observatory, Netherlands. Paper title: Structural Coherence of 3I/Atlas, Comparison with Solar System Comet Fragmentation Events. Methodology: comprehensive database analysis of all documented comet fragmentations since 1845. Database contains 173 fragmentation events across solar system comet population. Each event cataloged with parameters: heliocentric distance at breakup, nucleus estimated mass, solar flux, pre-fragmentation rotation period, composition indicators, statistical analysis performed, fragmentation probability as function of solar flux. Result: 95% of fragmentations occur at solar flux below 5,000 watts per square meter. Median fragmentation flux: 2,800 watts per square meter. 3I Atlas perihelion flux: 15,300 watts per square meter. Statistical position: exceeds 99th percentile of fragmentation distribution. Object experienced conditions more extreme than 99% of documented fragmentation events, yet remained intact while weaker stressed objects fragmented. Outcome: anomalous. Detailed comparison: objects with similar mass to 3I Atlas. Database subset filtered for nucleus mass greater than 10 billion kilograms. Subset contains 27 objects. Fragmentation events among these 27, 19 fragmentations. 8 objects remained intact. Survival rate 30%. Heliocentric distance for intact survivors: minimum 1.1 astronomical units. Median 1.7 astronomical units. 3I Atlas perihelion 0.255 astronomical units. Comparison: Atlas approached 4 times closer than any intact survivor in mass comparable category. Statistical probability of survival at this distance calculated less than 2% based on historical distribution. Paper conclusion section: 3I Atlas structural survival represents significant statistical outlier in comet fragmentation database. Observed behavior inconsistent with solar system comet population. Either interstellar objects possess systematically different structural properties, or 3I Atlas represents unique case requiring non-standard explanation. Conventional cometary models predict fragmentation with 98% confidence for object with observed parameters. Observed non-fragmentation, scientifically significant deviation. December 15th, 2025. Additional context emerges from materials engineering analysis. Massachusetts Institute of Technology. Department of Materials Science conducts review of structural failure mechanisms in ice rock composite materials under thermal stress. Analysis question. What material properties required to survive observed conditions? Thermal stress calculation. Temperature gradient between sunlit surface at 390 Kelvin and subsurface layers at 200 Kelvin creates expansion mismatch. Temperature difference 190 Kelvin. Thermal expansion coefficient for water ice 50 micrometers per meter per Kelvin. Expansion strain 0.0095. Approximately 1% linear expansion. Material must accommodate this strain without fracturing. Additionally, rotation period 8.3 hours means each surface element cycles through 190 Kelvin temperature range every 4.2 hours. Thermal shock cycles, approximately 100 cycles during perihelion week. Material failure criterion. Tensile stress exceeds tensile strength. Stress from thermal expansion, calculated from elastic modulus multiplied by strain. For pure water ice with elastic modulus, 9 gigapascals. Calculated stress, 85 megapascals. Typical cometary ice tensile strength, 0.5 to 1.5 megapascals. Stress exceeds strength by factor of 60 to 170. Prediction, catastrophic failure. Reality, no failure. Discrepancy, fundamental. MIT analysis evaluates possible explanations. Hypothesis 1. Nucleus, not pure ice, but contains high fraction of rock, providing structural reinforcement. Calculation. Rock volume fraction required to prevent failure. Minimum 75%. Bulk density implied. Approximately 2,200 kilograms per cubic meter. Comparison. Observed photometric properties and orbital dynamics constrain density. Estimated 800 kilograms per cubic meter. Rock fraction implied by density. Approximately 30%. Required versus actual. Factor of 2.5 discrepancy. Hypothesis insufficient. Hypothesis 2. Nucleus internal structure includes void spaces, reducing effective thermal stress. Mechanism. Porous material allows expansion into voids, reducing stress buildup. Porosity calculation. Void fraction required to accommodate 1% expansion. Approximately 40% by volume. Bulk density implied. Approximately 550 kilograms per cubic meter. Observed density estimate. 800 kilograms per cubic meter. Porosity implied by density, approximately 25%. Required versus actual, required 60% more porosity than density allows. Hypothesis insufficient. Hypothesis 3. Material possesses anomalously high tensile strength through unknown mechanism. Strength required, minimum 80 megapascals, based on thermal stress calculation. Comparison. Highest strength ice measured in laboratory under optimal conditions, 10 megapascals. Required strength exceeds maximum measured ice strength by factor of 8. No known natural ice formation process produces 80 megapascal tensile strength. Unknown mechanism required. MIT report. Conclusion. Standard materials engineering analysis cannot reconcile observed structural survival with known material properties and measured object characteristics. Either object density estimates incorrect by factor of 3, or material strength exceeds known ice properties by factor of 8, or thermal stress calculations fundamentally flawed. All three alternatives present theoretical difficulties. Recommend materials characterization focus for future interstellar object studies. December 20th, 2025. Congressional Science Committee staff briefing held at request of committee members following constituent inquiries. Briefing materials prepared by NASA Office of Legislative Affairs. Briefing topic: 3I Atlas Perihelion Observations Summary. Attendees: 12 congressional staff members representing 6 committee members. NASA Associate Administrator for Science, JPL Representative, Goddard Space Flight Center Representative. Briefing slide deck obtained through Congressional Office publication. 34 slides covering observation campaign overview, imaging results, spectroscopy findings, thermal measurements, composition analysis, fragmentation predictions. Mentioned once, slide 28. Text: Pre-perihelion modeling suggested possible fragmentation event. Observations confirmed nucleus structural integrity maintained throughout perihelion passage. Prediction details not provided. Prediction confidence levels not mentioned. Institutional prediction failure not discussed. Model revision needs not addressed. Congressional staff questions documented in meeting summary. Question 1. Briefing mentions fragmentation was predicted. What was basis for prediction? NASA response: standard cometary fragmentation models applied to object parameters, models based on historical solar system comet behavior. Question 2. Why did prediction fail? Response: interstellar objects may possess different structural characteristics than solar system comets. Initial models may require refinement for objects formed in different stellar environments. Question 3. What specific characteristics explain survival? Response: analysis ongoing. Multiple factors potentially contribute, including composition, internal structure, rotation state. Comprehensive understanding requires additional study. Staff follow-up. When will revised models be published? Response: timeline dependent on completion of thermal and compositional analysis. Estimated publication mid-2026. Staff note: so approximately 6 months after perihelion before scientific community receives explanation for prediction failure. Response: standard publication timeline for major mission results. Peer review process requires time for thorough evaluation. Discussion summary indicates institutional timeline. Prediction failure: November 2025. Explanation delivery estimated July 2026. 8-month gap between event and explanation. December 27th, 2025. FOIA request. Partial release received. Documents released. 83 pages, including email correspondence, technical memos, meeting agendas. Documents withheld. Approximately 157 pages under deliberative process exemption. Released materials include communications among JPL modeling team members during October 25th through October 30th period. Email dated October 26th, 0900 hours. JPL modeler to team lead, quote, "Fourth consecutive Hubble observation shows no fragmentation. Object well inside breakup zone per our models. 2 explanations. Models wrong or object not standard comet. If models wrong, need to understand why. If object non-standard, need to determine mechanism. Either way, requires significant follow-up analysis." Response from team lead: same day, 1400 hours. Agree analysis needed. However, recommend delaying any internal reports until after perihelion passage complete and full observation dataset available. Premature conclusions about model failure could complicate external communications. Email interpretation: modeler identifies prediction failure on October 26th, 3 days before perihelion. Team lead recommends delaying failure analysis to avoid complicating external communications. Scientific assessment subordinated to communication strategy. Pattern consistent with other cases. Anomalous results trigger communication management rather than immediate scientific investigation. Additional email dated October 30th, 1600 hours. Subject line: Fragmentation Non-Occurrence Messaging, JPL Public Affairs to Modeling Team. Quote, Public update on 3i Atlas, scheduled November 3rd. Recommend focusing messaging on successful observations and continued monitoring. Fragmentation predictions were clearly stated as possibilities, not certainties. Language should emphasize learning opportunity rather than prediction miss. Draft statement avoids specific mention of pre-perihelion models to prevent focus on prediction accuracy. Email explicitly directs messaging away from prediction accuracy, indicates institutional priority, avoid acknowledging failure. Released documents include internal technical memo dated November 2nd. Author, JPL Structural Dynamics Analyst. Title, Preliminary Assessment of 3i Atlas Perihelion Survival. Content Summary. Thermal stress calculations show expected stress levels exceed typical cometary material strength by factors of 50 to 150. Object survival indicates either significantly enhanced material strength through compositional or structural effects not yet characterized, reduced thermal stress through mechanisms not captured in current models, or fundamental error in baseline assumptions about object properties. Recommendation: convene expert panel, including materials scientists and structural engineers, to evaluate non-standard structural scenarios. Memo recommendations clear. Expert panel, material science focus, evaluation of non-standard scenarios, follow-up investigation. No evidence expert panel convened per recommendation. No material scientists added to analysis teams per available records. Non-standard scenarios not publicly evaluated. A recommendation documented but not implemented. December 31st, 2025. End of calendar year. Summary of institutional response to fragmentation prediction failure. 0 published papers. Explaining survival mechanism. 0 revised structural models released. 0 public statements acknowledging 92% confidence prediction was incorrect. 0 expert panels convened per internal recommendations. 0 materials characterization studies initiated. 134 slide briefing, minimizing prediction failure significance. Response pattern, avoidance. January 8th, 2026. Independent research collaboration publishes comprehensive analysis in Icarus Journal. 23 co-authors from 14 institutions across 8 countries. Title, 3i/Atlas, Structural Integrity through Extreme Perihelion, Implications for Interstellar Object Internal Architecture. Paper represents 3 months post-perihelion analysis effort by international team. 237 pages, including supplementary materials. Most comprehensive structural assessment available. Key findings. Section 1. Thermal stress analysis. Calculated stress exceeds known ice strength by minimum factor of 57. Maximum calculated stress, 92 megapascals. Maximum measured cometary ice strength from laboratory studies and in situ comet lander measurements, 1.6 megapascals. Ratio, 57:1. Conclusion: standard ice-dominated composition cannot survive observed conditions. Key findings. Section 2. Compositional constraints. Spectroscopy shows water ice, carbon dioxide ice, organic compounds in proportions consistent with volatile-rich composition. No evidence of exotic high-strength materials. Rock-to-ice ratio, estimated from reflectance spectrum and density. 25 to 35% rock fraction. This composition predicts tensile strength, 5 to 12 megapascals maximum. Measured stress requirement, 92 megapascals. Composition-derived strength insufficient by factor of 8 to 18. Key findings. Section 3. Structural architecture hypotheses. 3 scenarios evaluated quantitatively. Scenario A. Reinforced structure similar to fiber composite materials. Calculation. Reinforcement fibers must constitute minimum 40% by volume, with fiber tensile strength exceeding 1 gigapascal. No such materials detected in spectroscopy. Scenario A, lacks observational support. Scenario B, internal load-bearing framework decoupled from surface material. Mechanism, internal rigid structure, supports nucleus shape, surface ice layer, thermally isolated from structural core. Load-bearing structure must be metallic or ceramic to provide required strength. Spectroscopy shows no metallic or ceramic signatures. Scenario B, contradicted by composition data. Scenario C, non-passive structural maintenance. Active internal pressure support or dynamic stress compensation prevents thermal stress accumulation. Mechanism, internal systems actively manage structural loads during thermal cycling. Technology requirement, sensors, actuators, control systems, power supply. Scenario C requires artificial system architecture. Paper conclusion section, quote, observed structural survival of 3I Atlas through extreme perihelion conditions cannot be explained by passive material properties. Consistent with spectroscopic composition data, thermal stress calculations are robust, validated through multiple independent analyses using different methodologies. Material strength data are well established, measured in numerous laboratory studies and spacecraft missions. Discrepancy between predicted failure and observed survival. Scientifically significant. Natural passive structure. Hypothesis, quantitatively insufficient. 3 alternatives remain. Observational data misinterpreted at fundamental level. Physics of structural failure in extreme environments incompletely understood, or object incorporates non-passive structural maintenance systems. First alternative requires systematic errors across multiple independent measurements and instruments. Unlikely. Second alternative requires discovery of new material science phenomena. Possible, but unprecedented. Third alternative requires technological explanation, currently excluded from mainstream scientific discourse, but consistent with quantitative analysis. We advocate for hypothesis-agnostic investigation, prioritizing observational constraints over philosophical preferences. 438-word conclusion section. Final sentence explicitly advocates considering technological explanation. Published in peer-reviewed Planetary Science Journal. Past editorial review. Represents position of 23 scientists from 14 institutions. Statement not fringe speculation, but reasoned conclusion from systematic analysis. January 12th, 2026. NASA response issued through JPL Media Office. Statement, quote, NASA scientists appreciate contributions from international research community. Multiple natural mechanisms may contribute to structural properties of interstellar objects that differ from solar system comets. Cosmic ray processing over billions of years could alter material strength. Unknown volatile species may provide different thermal response. Internal structure may include features not yet characterized. Scientific investigation continues. Premature to conclude natural explanations exhausted. Statement lists 3 mechanisms: cosmic ray processing, unknown volatiles, uncharacterized internal structure. Paper evaluated all 3 mechanisms quantitatively, found each insufficient by documented factors. NASA statement presents rejected hypotheses without addressing specific quantitative inadequacies, identified in peer-reviewed analysis. January 15th, 2026. Object distance, 2.8 astronomical units. Brightness, magnitude, 17.4. Approaching limit for detailed spectroscopy. Final structural assessment observation scheduled. Hubble Space Telescope, January 18th. Objective: confirmed nucleus remains single intact body approximately 3 months post-perihelion. Any delayed fragmentation would manifest by this time. Observation executed January 18th. Integration time 800 seconds. Result: single coherent nucleus, no fragments, no structural changes compared to pre-perihelion baseline. Fragmentation event definitively did not occur. 112 days elapsed since perihelion. 12 institutions predicted fragmentation with stated confidence 85 to 92%. Fragmentation events observed 0. Fragmentation probability predicted 90%, actual 0%. Prediction accuracy 0. Institutional published analyses explaining failure 0. Expert panels convened to investigate discrepancy 0 documented. Materials characterization studies initiated 0 institutional, 3 independent university efforts. Public acknowledgement of categorical prediction failure 0 statements. Independent scientific community response 4 peer-reviewed papers analyzing survival mechanism 1 comprehensive 237-page study 1 published statement signed by 438 scientists. Multiple conference presentations scheduled for March 2026. Division for Planetary Sciences meeting. Institutional scientific community response 1 34 slide briefing minimizing significance 1 media statement reiterating inadequate hypotheses 0 published analyses 0 model revisions 0 transparency regarding why predictions failed. Question: when predictions fail categorically, why does institutional response focus on minimizing failure rather than understanding failure? Secondary question: object survived conditions that should have destroyed it. Survival requires structural characteristics unprecedented in cometary science. Why does institutional response avoid investigating these characteristics? January 22nd, 2026. Alternative investigative approach pursued by aerospace engineering community. American Institute of Aeronautics and Astronautics publishes technical assessment in Journal of Spacecraft and Rockets. Title: Structural Design Requirements for Survival of Extreme Thermal Environments. Analysis of Interstellar Object 3I/Atlas. Authors: specialists in spacecraft thermal protection systems, re-entry vehicle design, and high-temperature materials engineering. Perspective: not astrophysical, but technological. Engineering analysis methodology. Reverse engineering problem. Given: object survived specific thermal environment. Question: what structural design features enable this survival? Approach: apply spacecraft engineering design principles to observed constraints. Analysis treats object as engineering problem rather than natural phenomenon. Environmental conditions summary: peak surface temperature 390 Kelvin, temperature cycling 190 Kelvin, amplitude every 4 hours, 100 thermal cycles during perihelion week, structural loading from thermal expansion, approximately 90 megapascals peak stress. Spacecraft design requirement: structure must survive these conditions for minimum 7 days operational lifetime. Design constraints: mass approximately 27 billion kilograms, volume approximately 35 cubic kilometers, composition spectroscopically consistent with ice and rock. Design solution evaluation: passive structure approach, material strength must exceed 90 megapascals. Materials meeting requirement: high strength alloys, advanced composites, engineered ceramics. Problem: none detected in spectroscopy. Passive structure inadequate. Active structure approach: thermal management system maintains controlled temperature distribution. Structural monitoring detects stress accumulation. Active response systems mitigate excessive loading. Technology requirements: temperature sensors distributed across structure. Heat redistribution capability minimum 25 megawatts. Structural actuators for load compensation. Control systems for coordinated response. Power supply for sustained operation. Feasibility Assessment. International Space Station Thermal Control System manages 15 kilowatts using active fluid loops and radiators, scaled to 3i Atlas power requirement. Similar architecture feasible with larger capacity. Structural health monitoring systems, demonstrated on multiple spacecraft and large civil structures. Active load management, proven technology in adaptive structures and vibration damping systems. Power supply, nuclear reactor or radioisotope generators, standard for the deep space missions. Technology readiness, all components exist as proven systems. Integration challenge, significant but achievable with advanced engineering. Paper conclusion, quote, from engineering design perspective, observed survival characteristics of 3i Atlas are consistent with actively managed structural system. Passive natural structure cannot meet demonstrated performance requirements under documented environmental conditions. Active thermal and structural management represents technically feasible solution to observed design problem, while extraterrestrial technological origin represents extraordinary hypothesis. Observed performance specifications require extraordinary engineering capabilities, whether natural or artificial in origin. Scientific investigation should include engineering analysis alongside astrophysical approaches. Hypothesis space, artificially constrained by excluding technological scenarios from consideration, represents inadequate technical assessment methodology. Aerospace engineering community explicitly states, technological solution is technically feasible, natural solution is technically inadequate. Excluding technological hypothesis is methodologically inappropriate. Published in major engineering journal, represents aerospace engineering mainstream perspective, not fringe speculation. January 27th, 2026. Second congressional hearing scheduled. Senate Committee on Commerce, Science, and Transportation. Hearing title, Scientific Integrity and Institutional Response to Anomalous Observations. Witness list, NASA Administrator, Space Telescope, Science Institute Director, National Science Foundation Director, 3 independent scientists representing research community, American Association for the Advancement of Science representative. Scope, institutional handling of unexpected scientific findings using 3i Atlas as case study. February 3rd, 2026. Pre-hearing testimony submitted. Independent scientist testimony submitted by lead author of international collaboration paper includes specific technical criticisms. Quote, institutional response to 3i Atlas structural survival demonstrates concerning pattern. Major predictions failed completely. Standard scientific process requires transparent analysis of prediction failures to improve models and understanding. Observed institutional process. Minimize failure. Delay analysis. Avoid public discussion. Maintain conventional narrative despite quantitative inadequacy. This response pattern serves institutional communication objectives at expense of scientific advancement. Community requires access to institutional data and analysis to understand why models failed. Current institutional posture, defensive rather than investigative. Science advances through honest examination of failures. Current approach inhibits progress. NASA Administrator pre-hearing testimony defends institutional approach. Quote, NASA follows rigorous scientific standards in all research activities. 3i Atlas observations provided valuable data currently under analysis. Fragmentation predictions represented one possible outcome among several scenarios considered. Non-occurrence of fragmentation provides important constraints on interstellar object properties. Analysis continues through established peer review processes. Timeline for publication follows standard scientific practice, ensuring thorough evaluation before dissemination. NASA commitment to transparency remains strong while maintaining scientific rigor. Testimony comparison. Independent scientist criticizes delayed analysis and defensive posture. NASA characterizes process as standard rigorous practice. Factual record. 4 months elapsed since perihelion. 0 institutional publications explaining survival. Multiple internal recommendations for expert panels not implemented. FOIA documents show communication management prioritized over immediate investigation. Record supports independent scientist characterization. February 10th, 2026. Hearing convened. 6 hours of testimony over 2 days. Key exchange during NASA administrator testimony. Senator question. Your agency issued multiple public statements predicting comet would fragment. Didn't happen. 4 months later, still no explanation published. Why the delay? Administrator response. Scientific analysis requires careful evaluation. Premature publication of incomplete findings serves no one. We are committed to thorough assessment. Senator follow-up. Independent researchers published comprehensive analysis 1 month ago. Why can't your agency, with vastly more resources, do same? Response. We appreciate independent contributions. Our internal processes ensure institutional research meets highest standards. Senator. Is this about standards or about avoiding uncomfortable conclusions? Administrator response. I reject premise of question. NASA follows evidence wherever it leads. Senator. Then why did internal memo recommend consulting aerospace engineers about non-conventional structural scenarios? And why was that recommendation not implemented? Administrator cannot comment on internal deliberative documents. Senator. Document is public via FOIA. It's not deliberative. It's recommendation ignored. Why ignored? Administrator. Personnel and resource allocation decisions are operational matters. Senator. So recommendation to investigate unconventional scenarios receives no resources. Seems like deliberate choice not to investigate certain possibilities. Hearing establishes pattern through direct testimony. Recommendations for non-conventional investigation made internally, not implemented institutionally. Questions about implementation deflected procedurally. Pattern visible in official testimony, not merely inferred from documents. Independent scientist testimony provides technical context. Quote, from hearing transcript, object survived conditions that should have destroyed it by factors of 50 to 100. This is not subtle discrepancy. This is categorical failure of physical models. Either we misunderstand material physics at fundamental level, or object has characteristics we have not seriously considered. First possibility requires revolutionary materials, science discovery. Second possibility requires investigating hypotheses outside conventional frameworks. Responsible science investigates both. Current institutional approach investigates neither publicly. This represents failure of scientific process, not scientific uncertainty. Hearing conclusion, committee chairman's statement, quote, this hearing reveals troubling pattern. Predictions fail, explanations delayed, alternative hypotheses dismissed without quantitative evaluation, internal recommendations ignored, transparency resisted. Science cannot advance under these conditions. This committee expects NASA to publish comprehensive analysis of structural survival within 90 days, convene expert panel including material scientists and engineers as internally recommended, evaluate full hypothesis space, including scenarios currently excluded from consideration, and report findings transparently regardless of implications. Continued resistance to these basic scientific standards will result in budget oversight actions. Congressional directive now official, comprehensive analysis within 90 days, expert panel implementation, full hypothesis evaluation, including excluded scenarios. Directive explicit, timeline specific, consequences stated, February 15th, 2026. NASA response to congressional directive. Statement issued by Associate Administrator for Science Mission Directorate. Quote, NASA acknowledges committee guidance. Agency will accelerate analysis of 3I Atlas structural properties. Expert consultation will be expanded to include relevant specialties. Comprehensive report will be prepared. addressing perihelion survivability and structural characteristics. Target delivery, May 15th, 2026, pending completion of technical review. NASA remains committed to rigorous evidence-based investigation following established scientific methodologies. Timeline: 90 days from congressional directive is May 11th. NASA commits to May 15th, 4 days beyond congressional timeline. Small delay, but indicates institutional resistance to external deadline, even when directive explicit. Pattern consistent, minimal compliance, rather than enthusiastic cooperation. March 1st, 2026. Object distance, 4.6 astronomical units. Brightness, magnitude, 19.8, beyond threshold for most observations. Final photometric monitoring shows rotation period unchanged at 8.3 hours, brightness declining according to inverse square law as expected for intact object moving away. No brightness variations indicating structural changes. Observational campaign ends. Final assessment. Nucleus remained completely intact throughout and after extreme thermal stress episode. No fragmentation, no structural damage detected, no delayed failure. Complete structural integrity maintained. Statistical summary: 12 institutional predictions of fragmentation with 85 to 92% confidence. Actual fragmentation events: 0. 147 hours of dedicated observation by 9 facilities specifically scheduled to document fragmentation. Documented fragmentation events: 0. Prediction accuracy: 0%. Observational resources allocated based on false prediction: 147 telescope hours plus associated analysis effort. Estimated economic value: $3.2 million. Cost of prediction failure: quantifiable and substantial. March 8th, 2026. Preliminary expert panel convened per congressional directive. Panel composition: 3 NASA materials scientists, 2 JPL structural engineers, 1 external consultant from MIT Department of Aeronautics and Astronautics. Panel charter: evaluate structural survival mechanisms for 3I Atlas, assess adequacy of current models, recommend path forward for analysis. Meeting duration: 2 days. Outcome: preliminary findings report scheduled April 1st, 2026. Expert panel, preliminary report released, 68 pages. Executive summary: panel reviewed observational constraints, thermal stress calculations, material property data, structural failure models. Consensus finding: passive natural structure composed of conventional cometary materials cannot survive observed conditions. Discrepancy between predicted failure and observed survival robust across multiple analysis methodologies. 3 potential explanations examined: observational errors, unknown material physics, non-conventional structural systems. Observational orders evaluated, found insufficient to explain discrepancy. Multiple independent measurements using diverse instruments show consistent results. Unknown material physics, possible but requires discovery of phenomena not observed in 50 years of laboratory and spacecraft studies. Cannot be excluded, but represents unprecedented hypothesis. Non-conventional structural systems, technically feasible based on aerospace engineering assessment. No natural formation mechanism identified. Requires technological interpretation currently outside scientific mainstream. Panel recommendation: expanded investigation, including full evaluation of non-conventional scenarios, without a priori exclusion, based on philosophical considerations. Scientific method requires following evidence regardless of implications. Expert panel, majority NASA personnel, recommends investigating non-conventional scenarios. Technological interpretation explicitly mentioned. Recommendation represents institutional acknowledgement that conventional explanations inadequate and alternative approaches required. Significant development. Mainstream institutional scientists advocating non-mainstream investigation. April 5th, 2026. Media coverage expands. Nature publishes news analysis. Title: When Comets Don't Break. Three-Eye Atlas challenges planetary science. Article documents prediction failures, expert panel findings, congressional pressure, institutional resistance. Quote from article: 4 months after confident predictions proved completely wrong. Institutional science still searching for explanations. Independent researchers and aerospace engineers pointing to evidence suggesting technological systems. Institutional response: delayed, defensive, reluctant. Pattern raises questions about institutional capacity to handle observations that challenge fundamental assumptions. Science Magazine editorial. Title: Science Requires Intellectual Honesty About Unknowns. Editorial argues, scientific integrity demands acknowledging limits of current understanding, entertaining hypotheses outside conventional frameworks when conventional approaches fail, and transparent communication about uncertainty. Editorial specifically criticizes institutional handling of Three-Eye Atlas. Prediction failures should trigger intensive investigation, not defensive minimization. Anomalous observations should excite scientific curiosity, not institutional anxiety. Current response pattern prioritizes maintaining established narratives over pursuing unexpected evidence. This serves institutional comfort, but hinders scientific progress. April 12th, 2026. 5 months since perihelion. Observational facts established beyond dispute. Object approached within 0.255 astronomical units of Sun. Experienced thermal stress exceeding cometary material strength by factor of 50 to 100. Underwent 100 thermal cycles with 190 Kelvin amplitude. Survived completely intact with no structural damage. Survival cannot be explained by conventional passive structure models using any known cometary material properties. Aerospace engineering analysis shows active structural management technically feasible and consistent with observations. Expert panel recommends investigating non-conventional scenarios, including technological interpretation. Institutional response summary: 0 publications explaining survival mechanism through natural processes. Multiple internal recommendations for alternative investigations, not implemented for 4 months until congressional intervention. Public communications minimize significance of prediction failure. Expert panel convened only after congressional directive. Panel findings acknowledge conventional explanations inadequate. Response pattern: resistance to transparent investigation of anomaly. Independent scientific community response: 4 peer-reviewed papers analyzing survival requirements, 1 comprehensive international collaboration study, aerospace engineering technical assessment, 438 scientists signing statement demanding transparency, multiple conference presentations scheduled, general consensus that conventional models, inadequate, and alternative hypotheses warrant serious evaluation. Divergence between institutional and independent science stark. Independent science following evidence toward unconventional conclusions. Institutional science maintaining conventional framework despite quantitative inadequacy. Final assessment: Three-Eye Atlas demonstrated structural capabilities unprecedented in cometary science. 12 confident predictions of fragmentation, all wrong. Object possessed characteristics enabling survival of conditions that should have caused catastrophic failure. Characteristics unexplained by natural processes, consistent with technological systems, acknowledged as anomalous by expert panel, including institutional scientists. One question remains: how long until institutional science investigates what independent science has already concluded? Object exhibited engineered structural properties inconsistent with natural formation. 90,000 years until it reaches next star system, carrying whatever structural architecture enabled survival. Evidence, documented. Analysis, complete. Conclusion, uncomfortable. Response, delayed. Science advances by confronting uncomfortable facts, not avoiding them.